All right, in this video, we're going to be taking a look at different functions and their graphs, what they look like. So let's go ahead and get started. So looking at the definitions, all of these definitions you should already know up to this point. So go ahead and take a minute and just think about what these definitions mean and try to write definitions, your own definitions of them. So we have relation, function, independent and dependent variable, then domain, range, and then the term evaluate. Go ahead and write your own definitions, pause the video, and then come back. All right, so let's talk through these definitions. Like I said, you should already know what they are at this point, but let's just kind of walk through them. A relation is kind of like a set of ordered pairs, like X, Y is a relation, and just kind of a relation is how they're defined together, right? And a relation is shown in terms of functions. A function is the thing that defines a relationship between ordered pairs. A lot of times a function can be y equals, or function notation is f of x, meaning you can plug stuff into it. So relation, function, independent variable. The independent variable, that is your x value, right? That is the variable that does not depend on the other variable or variables in the relation. And your dependent is your y. It does depend on the other variable or variables in your relation. And independent variable, which is x, is also the domain, and the y is your range. Another term for domain is input. Another term for range is output when you're talking about function notation. And then the word evaluate, well, that just means to plug in, right? A lot of times you evaluating expressions are in terms of function notation, you're plugging values in. It doesn't necessarily mean the same thing as solving. A lot of times when you use the term solve, that means get x by itself. But evaluate, a lot of times you're plugging stuff in. Talk about these functions that are defined implicitly or explicitly. What are they and how can they be identified? Well, first of all, when a function is implicitly defined, right here, that means x and y cannot be separated, right? A lot of times when you want to solve or even evaluate functions, you want to get x or y by itself so that it's y equals. But if it's implicitly defined, you cannot do that. It makes it impossible. So later on this year, we're going to learn, well, how do we find the derivatives or integrals of functions that are implicitly defined, right? And if it's explicitly, then it can be separated. It's much easier to work with. And how can they be identified? Well, one way that they can be identified, number one, just try to solve it. But a lot of times, if you have like y cubed and then another y, something like this, you cannot separate those, okay? Because y is your dependent variable. That's, the y could be independent, but it's not. So if it's your dependent variable cannot be solved to get by itself, then it's implicitly defined. Okay, so evaluate was one of the definitions, if possible, because sometimes it's not possible. You have to be really careful, especially with these transcendental functions, sine, cosine. Evaluate the function at the given values of the independent variable. So this is what you're plugging in. So go ahead and try these. Look at your unit circle to answer some of these questions. Try not to plug it into a calculator. So pause the video, try these, and then come back. Okay, on part A, you're plugging 0 in, so it's going to be the cosine of 2 times 0. And that's the cosine of 0, which is just 1. And then on B, you're plugging negative pi over 4 in there. So that would be cosine of 2 times pi over 4. Oop, that's a 4. That'll cancel that's a negative. And that'll simplify to cosine of just negative pi over 2. There we go. And that is just 0. Again, look at your unit circle, or think of your unit circle to answer these. Don't plug them into a calculator. Then you would have the cosine of 2 times, so we did this one, and this is pi over 3. So you're looking at the cosine of 2 pi over 3. Looking at your unit circle, that is negative 1/2. So evaluate, just plug it in, and then simplify. An example dealing with the domain and range. So here it says find the domain and the range of this function. Go ahead, remember, domain is x, range is y. Go ahead and try this on your own, or in this case, depending, they can use different variables. Just remember, domain is your input, and the range is your output. Go ahead and find the domain and range, write it however you want. There's a couple different notations, and we'll kind of talk about that. Pause the video and try this on your own. All right, so let's see how you did. In this case, the domain, all of the possible x values, right? So if you think about, what I like to do is just capital D with a semicolon there. So the domain, all of the possible x values, well, sometimes it's not limited, but in this case, square roots, you cannot have a negative square root. So in order for the domain to exist, anything under here, so this x plus 3, right there, that has to be greater than 0. So x plus 3 has to be greater than 0. So x has to be greater than negative 3. So I said one thing and wrote another. All right, so one way you could write it is that, hey, x has to be, or equal to, it can be 0, I guess. So x has to be greater than or equal to negative 3. That's one way to write it. Another way to write it with brackets and parentheses, so, or it can go from negative 3, any value from negative 3 to infinity. And these brackets right here, that is inclusive of that value, means it can include negative 3. And then with infinity, you always use a parenthesis, never a bracket, since infinity is a concept, not a number. All right, so then that would be our domain, and our range, you'd have to think, okay, well, what's our lowest y value or highest y value that we could get? And that would be 0. And it's going to be our highest y value because of that negative in front there. Our range is going to be any value that is less than or equal to 0. Those are all the y values we could get. Or if we write it in set notation form, it'd be from negative infinity all the way to 0, and it includes 0 because we could get 0, so we include that value. Try it again on this next one. Find the domain and range. Think about rational expressions. Think about what x or y could or could not be, and then write your domain and range. Pause the video, go ahead and do so, and then come back and try it, and then see how you did. All right, so thinking about our domain, again, we're going to write our domain and range over here. Thinking about the domain, the denominator cannot be 0. So if you set x squared minus 4 not equal to 0, and then you would add 4 over, so you get x squared cannot be 4, so x cannot be positive or negative 2. Right, so that's one way. So x can be all reals, except x cannot be positive or negative to 2. Or you can write that with your parentheses and brackets. That's called set notation. So it would be any number from negative infinity to negative 2, unioned with the set from negative 2 to 2, unioned with the set from 2 to infinity. And you are not including negative 2 and 2, which is why there are no brackets in there. They're all parentheses. Okay, now taking a look at your y values or your range values. looking at what the lowest possible could be and the highest possible. In this case, since it's all positive, right, your lowest is going to be from 0, and then it can go upwards from there, because you could have 1 over anything but 0, right? So we cannot include 0, but 0.00001 could be one of them, maybe a number close to 0 but not equal to 0, and so it'd be from 0 to infinity on that one. All right, so there's different ways to write domain and range. I guess on this one it just says find the domain, but anyway, there's different ways to write the domain and range of functions. If I had to choose a favorite, well, I like both of them. Like, I would say that is a lot easier, but this is a more thorough explanation of the domain and range, right? So it depends on what the question is asking, if they want a thorough explanation or just a simple answer the question. So now let's take a look at piecewise functions. I call them or refer to them as Frankenstein functions. Right, because basically piecewise functions are pieces of other functions that are just put together to create one function. So it's pieced together, functions that are pieced together. And a lot of times they're written like this. So here is a piecewise, where on this first part it says use x squared plus 2 whenever x is less than or equal to 1. And on this next part it says use x squared plus 2, or sorry, 2x squared plus 2 wherever x is greater than 1. All right, so they're pieced together and they come, whether they meet up perfectly or not, I don't know, but they come together at x equals 1. All right, so now let's take a look at answering some questions. If you know how to do these, go ahead and try A through D. Pause the video and then come back and see how you did. All right, so let's see how we did. We're plugging -2 in there. So then you have to think, am I going to be using the first function or the second function? Well, we're going to be using the first one because it states use this one whenever x is less than or equal to 1. So we're going to use the first one. So it's going to be -2 squared plus 2. That's going to be 4 plus 2. It's going to be 6. Okay. And then on B, we're also going to be using the first one because it's a value that is less than or equal to 1. So it'd be 0 squared plus 2, which is just 2. And we're also on this one going to be using the first one because it's equal to 1. And it would be 1 squared plus 2. And so then that would be just a total of 3. Now, on the last one, the tricky part is which one are we going to be using? Well, we are going to be using the second portion because whenever you square something and add 2, no matter what you're squaring, you're always adding 2. All right, when you square something, it's always going to be positive. So whenever you add 2 to that, it's going to be a number that is greater than 1. So we know that we're going to be using the second one. So we're going to be using the 2x squared plus 2. And so it looks like this. So f of your s squared plus 2, we're plugging that right in there. So that would be 2 times s squared plus 2 plus 2. Okay, you can simplify, oops, this is squared because of that. You can simplify that if you want to, but I'm just going to leave it right there. Okay, because if there's an s in there, we can't get a numerical value anyway, so that's good enough to keep it right where it's at. Now looking at the graphs of functions and all the parent functions that you need to be familiar with, there's more as well if you look on the next page, but on this one we're going to be looking at the most simple ones. So you have y is equal to x, or f of x is equal to x squared, x to the third, and square root of x. Go ahead and copy down what you think the parent functions will look like of these graphs. Pause the video and then come back. All right, so this is what our graphs are going to look like. The first one is a linear graph, so it's just a straight line through the origin with a slope of 1. The next one is your quadratic. This is a cubic, so it looks something like that. And then the square root, now if it's positive, negative square root, it would look like this. But in this case, I just wrote square root, so it's just the upper portion. But if it's positive, negative square root, it would look like that. Okay. Then looking at the next set of graphs that you need to be familiar with, you need to be familiar with the absolute value function. So this would be the absolute value function. Also 1 over x, sine of x, and cosine of x. Go ahead and sketch these graphs and then come back to the video. Okay, the absolute value function is actually a piecewise function in disguise because you have all of the positive x values for y equals x and all of the negative x values for y equals negative x. And that's what creates our absolute value. Looks like a v. And then the 1 over x looks like this one here. Then you have sine, which it starts at the origin. But cosine, its max is at the origin and then goes down from there. All right, so be familiar with all of those parent functions, moving them around. And then also the basic types of transformations. Now this is in your book, you can copy them down. I'm going to go ahead and pause the video, write them down so that we can talk about them. So here are all of the different types of transformations, kind of going down the list here. With this first one, that's just your parent function. There's no transformation there, okay? But looking down under that, that is where it's going to be c units to the right. And then the next one is c units to the left. Okay, so moving right and left, it's opposite of what you would think, but when the c is being added or subtracted to the function itself, it's up and down. So if it's negative, this would be c units down. And this would be c units up. And then if it's negative on the outside of the function, right, your y is negative, not your x's, not your input, your function itself is negative. That's a reflection about the x-axis. And then if your x is negative, that is a y-axis reflection. Right, and then if they're both negative, that is an axis or a reflection around the origin. All right, so those are all of different types of transformations that you can apply to functions. Down here we have some more definitions. Go ahead and take a moment and see if you can't write out what these definitions are from your memory, what you remember of them, or what they were when you learned them first. Pause the video, try that, and then come back, and then we'll talk through them. Okay, so let's go ahead and look at these. So elementary functions, there are 3 types of elementary functions. Elementary doesn't mean simple at all. It's just elementary functions means basic. Basic does not mean simple either. Probably most common is a better one. But algebraic. Number 2 is trigonometric. And then 3 is exponential or logarithmic. There we go. Or exponential. Those are the 3 types of elementary functions. Polynomial functions, that's an algebraic. That is the most common algebraic function. So polynomial functions, those are the most common algebraic functions. And then all parts of your polynomial functions, you have the coefficients, leading coefficients. So if we write just a basic polynomial function, it would be like a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 and so forth, right? All the way to the very end where you would have your very first term. Okay, that a sub 0, that is your first term. Now, the coefficients, these are, let me highlight in yellow, the coefficients are those terms, those numbers being multiplied to your variables. So those are your coefficients, okay? Now, your leading coefficient right here, that is your very first coefficient when it's in order, when it's in standard form, your highest to lowest exponents, your first coefficient is your leading coefficient. And then your constant is that what it could be a coefficient, but it doesn't have a variable. That is a constant, just a number, no variable. And then all of these are terms. So when we're talking about terms, you have first term, second term, third, fourth, fifth, and then the final term, whatever nth term that is. We don't know in this case. And a rational function, well, that's just a function that can be written a lot of times as a fraction even. You'll see rational functions written as fractions. And then algebraic function, we've talked about that already right here. That's a lot of when you have variables in there. Transcendental functions, those are your sine, cosine, or trigonometric function. That's just a fancy way of saying trig function, right? When you have sine, cosine, tangent, cotangent, secant, cosecant, those are transcendental functions. Okay, good job on those definitions. And let's look to see what's next. Composite functions. Now, in rockology, or a lot of people call it geology, right? The study of rocks. Composite rocks, or rocks that are layered, right? One rock is made up of many rocks over time, where it's just layered upon each other. And so it's the same idea with functions. It's functions that are layered over and in each other. So functions that are, I'll just say, functions that are layered, right? In this case, it's going to look like functions inside other functions. That's how you identify composite functions. Looking at these down here, these are examples. You have your f of x and your g of x. They are separate functions, but you look at a through f, we're plugging numbers inside functions and then plugging that inside of another one. All of those are examples of composite functions. Go ahead and try a through f on your own and then pause it. So pause the video, try it, and then come back and see how you did. See how you did here on the first one. Let me still see those. You're plugging, figuring out what g of 2 is. So you're plugging 2 into your g function. That's where the pi times 2 comes from. And then that's, I just wrote that as 2 pi. Then you're taking it and plugging it inside your f of x. So that's where this comes from. And then you would have sine of 2 pi, which is 0. On the second one, it's all the same thing. You plug 1/2 into g, evaluate that, and then you get pi over 2. Plug that into your function, so you get sine, the f of x function, so you get sine of pi over 2, which is 1. And then part C, again, same thing, but you end up getting 0 on that one, because you end up with pi times 0. And then on D, you now figure out what is pi over 4 in my sine function first, and that's radical 2 over 2, and then plug it into my g function, so it's going to be pi times x, or radical 2 over 2, and you can keep it as pi times radical 2 over 2. I just rewrote it as square root of pi, square root of 2 times pi all over 2. And then your last two are pretty easy. You're just plugging one, just a straight up plug one inside the other. So you get sine of pi x and then pi times the sine of x. All right, so that's what composite functions are. They're not that difficult, but if they're new to you, they could be a little bit tricky to work with. All right, and then that's it for these notes. Hopefully this is making more sense. We're getting ready to get back into some heavy math with calculus. So this is just a quick review, one chapter review of the most important things from Algebra 1, Geometry, Algebra 2, and then Trig last year. So hopefully this made sense. Thanks for watching.